the presentation is about using Lagrangian neural networks to learn physics. I'm Abdullah Tamzolere. So I'm generally interested in computational tools to discover more theoretical frameworks for natural sciences in general. So mostly theoretical physics, and I hope to demonstrate how you can use computational tools such as artificial intelligence and neural networks in this case to actually learn something about the theory. And this project was this project was developed by the way, there is a discrepancy. I see something different. Sorry. Okay, this project is developed. Actually, Lagrangian Neural Networks is from 2020. It's from a conference paper in ICLR. It's a conference on machine learning. But combining it with symbolic regression was done by me and arkadaş Özakın in spring this year, actually. So that's what I'm going to present. The general outlook is I will first need to go through the neural background, which will be hard because there are computer majors and physics majors, and I will have to explain the Lagrangian part to some and the neural network part to some at the same time. And then we will go through the Lagrangian neural networks in general. Then we will combine it with the symbolic regression. Then we will talk about the general implications, and it will be over in that case. So yeah, let's start. Let's first talk about the history of a very brief history of the principle of least action. So actually, the principle of least action was first motivated through the light, the path of the light. For example, so actually 2,000 years ago, Hero of Alexandria was in the first historically known person to state that light takes the shortest path in general. But then we discovered actually it doesn't take the shortest distance. For example, here the shortest distance would be just a straight line, but it actually bends, and it's a longer distance in general. And around 1600s, Fermat, I don't know how to pronounce actually. Fermat hypothesized maybe it actually takes something of the least, but it's the time. So it takes the least time. Then he actually, 8 years later, he actually found that you can derive anything that we knew about light in that age if you just accept that it takes the shortest time. So it's the first time that we have seen nature actually exhibits at optimizing behavior, which is very strange. It seems like, I don't know, unmotivated in the first glance. Actually, in the second glance as well. So also there was also one more problem, which is Brachistochrone problem, which means shortest time problem. It's about an object going from A to B. We are trying to find the curve that minimizes the time that it takes under a constant acceleration. So this was first solved by Johann Bernoulli by actually relating this problem to the light problem that we have seen. He had shown that if you think that this object was like light and the medium was constantly changing, actually you can show that this will behave like a constant acceleration. The particle will behave like a constant accelerated particle, and then you can just apply the Fermat's shortest time principle, which actually practically you don't apply it in this case. You just apply Snell's law, which you see throughout the courses. So somehow matter, which has a mass, was related to light in the optimizing behavior, and it was a interesting parallel in this case. So later, one of his students, Maupertuis, which is hard to pronounce, again French, theorized some principle of optimizing behavior again in nature. So his theory was very intuitive. He said that the paths that we will see in nature will obey some kind of law that will minimize what he called action. So let's try to actually think about what action can mean. His action is very intuitive, but later actions are not very intuitive. So for example, let's draw. Hopefully this is a nice one. Okay. For example, we have a particle which goes from x1 to x2. Our theory is that it will take the less dramatic path in here. So, for example, I will ask some suggestive questions to you, and we will try to derive what he thought as the least action path. For example, I can go like this and go around like this, or maybe I can go with a shorter path. Which one do you think will be the less actionless path? Second, yeah, okay. We want to minimize our distance, let's say, from going from x1 to x2. What else? So let's say I'm taking this route, but I'm taking it very fast, or I'm taking it like slowly. Which is more actionless, more dramatic again? The fast is more dramatic in this case. So actually, his theory was also included the speed along with the distance. So we have distance and speed. Also, for example, think about a fly going through this route, or truck going through this route. Which one do you think is more actions again? So it's the massive one. Massive one is the more actionless one. So his theory was very simple in this case, and his action definition is just m times v times s, which s means in this case distance, and we will sum over different. For example, if we increase the sum of the parameters along the route, we have to sum them up separately. So this is the first least action principle that was shown, and in his time it was ridiculed and it was said it's not even true. But okay, so maybe it will be okay. One important thing is that he didn't provide anything to actually minimize any path. He didn't include any mathematical method to solve this path. He just said that the path it will take is this. And later Euler actually, near Maupertuis' life, liked this idea and tried to investigate whether or not it's true. And it turns out that it's true under some conditions, which is you have to, along this path, you have to have the same total energy, and that's it actually. So somehow this intuitive action is really happening in nature. So along with Lagrange, Euler actually showed how to solve this problem. First, he actually got rid of the summation with an integral, because we can change at any point, not just at discrete points like this. And then he actually showed how to how to minimize this. But we will just so some of you have seen the modern form of the action in the classical mechanics. So let's first start with this and try to get the modern form of the action. So we first, make it continuous. Then we substitute Vs with Vdt. Those are not very important, so I will just skip this, going through those steps. So you go through those steps. You actually add potential and decrease the potential. So this is the total energy, and this is T minus V. The total energy, as I said, as a precondition, is fixed. And I didn't motivate it right now, but anything which is constant is not important in this formulation, so you can just ignore it. I will actually show it that it's okay to do that. So you can get this. So this has little different forms. You have to actually know the end time here, for example, end time and the standing time for this to be true. But those are very similar, and this is the kinetic minus. By the way, I didn't say that, but this is kinetic energy, and this is the potential energy. So somehow what we did earlier is related to this kinetic minus potential. We are minimizing this integral somehow, and yeah. So one more thing is Euler and Lagrange actually provided a general approach. So you can have anything inside the integral. You call this the L, the Lagrangian, and then I will not derive it, but they derived it as if there is something like this, minimizing the action. To minimize the action, we have some conditions on L. So if L obeys some kind of equation, we can show that the action will be minimized, and this is called the Euler-Lagrange equation. So this is it. This is the Euler-Lagrange equation. I pulled it out of the thin air, but I can provide resources if you are interested more about this.
Yes. So did we just replace T minus V of x with L here?
Yes, L is more general form because T minus V does not generalize actually. Like it's stuck in the classical mechanic mindset, but L is more general. We will see again. So there is also a small caveat. We are saying it's the principle of least action, but our actual technique doesn't have to minimize it. It just, for example, when you set the derivative to 0, you can be maximizing it, or maybe you can be in a saddle point. So we don't know about that. The more true term is, although it's a small thing, the principle of stationary action. It's not very important. Sorry. Okay. So let's go. By the way, is there a question? Okay. Let's go through the Lagrangian mechanics. What is it? First of all, Lagrangian mechanics is a detachment from Newtonian mechanics, which usually involves forces, and you have to calculate the vectors, and you have to integrate to get energy, momentum, or whatever you want. The Lagrangian mechanics is built on the Lagrangian function. So Lagrangian function has to obey this formula. And in our case, L was equal to kinetic minus potential. So this is the form. And so let's plug this L to this equation and see what pops out. And this is also not very important, the details. So if you do actually plug this in and get this to the form. One more thing that I forgot is Q is the generalized coordinates, which you can just think about it as x, for example, here, and Q dot is the velocity, generalized velocity, which you can think about as v. Yes, you can recognize it from this as well. So, what is it? Potentials derivative. Actually, if it was higher dimension, it was going to be the gradient minus the derivative of the potential with respect to the position is actually the force that we have. So this is actually a very familiar expression that we all know. It's the F equals ma in this case. So why did we go through all of these to come back to F equals ma? Well, it has certain advantages, and first advantage is, for example, you have a complicated problem. The default example is double pendulum, and we will come back to that example later on again. Double pendulum is very hard to solve in Newtonian mechanics, but in Lagrangian mechanics, you just have to know the kinetic and potential energy, and you actually know how to solve it. This is called the equation of motion, which means that if you solve the differential equation, you can find any particle's future path, even the past path. So this is a very useful equation. So one advantage is you don't have to deal with the details of the system. You just have to know the energies, and it's just this. Plus, one more thing, which is very important, Lagrangian is kind of a central object. If you know this Lagrangian of a system, then actually you know everything that is relevant about the object. So, for example, you can find the momentum as the derivative of the Lagrangian with respect to the velocity, energy with this, and angular momentum with this. So everything you want is actually about in Lagrangian. So Lagrangian is a central object. It's kind of similar to the quantum state in quantum mechanics, but it's not the topic of this this seminar. So also the Lagrangian formalism generalizes, unlike the Newtonian one. There is a special relativity Lagrangian, general relativity Lagrangian, even quantum mechanics Lagrangian, and even particle physics Lagrangian, which you may have seen is the standard. So there is a standard model particle physics Lagrangian, which is like in everything that CERN cells, if you have seen like the big equation.
In all these scenarios, are we using that kinetic minus potential formula?
No, in just classical mechanics, it's just that true. Because this is related to some kind of an expression like this, and this was our hypothesis, and we have to include additional symmetries of the system to generate other kinds of Lagrangian in other systems. So it doesn't generalize in this case.
So it can be somewhat arbitrary under some certain conditions.
What?
So it can be somewhat arbitrary under some certain conditions.
Yes, it's usually arbitrary, by the way. You assume that it's going to be quadratic, or it's usually like this. So one question is the Lagrangian unique? If I have L prime as a constant multiple of L plus a constant additive to L, which is not the most general form of this uniqueness, but it's just a demonstration. Let's plug this to the Euler-Lagrange equation, which is very boring, so I did it in one step. So you can see that K doesn't matter, and C doesn't matter because we can divide by K. So if K is not 0, so it's not unique. The central object is not unique, first of all. And this is the same equation that we have started with. So that actually justifies what I did like 2 or 3 slides back. I said that the total energy is constant, so I will ignore it because it doesn't matter in the Euler-Lagrange equation. So we will now go to the neural network part, which is just jumping out of the topic. If you want to refresh your tea, or if you have a question, you can ask and you can go.
In some slides before, you said that from the summation formula, Euler turned it into an integral formula. And I want to ask, in maybe some certain scenarios, can we still use that summation formula, or we have to use the integral formula for all possible cases?
It's a good question. I don't know. In quantum formulation, I still remember there's integrals. So that is the most possible thing to have summation signs, but I still remember integrals there. So I don't know.
So it's not, so maybe it somehow works in only the discrete scenarios, which are not applicable in real world.
Maybe also early Lagrange equations, as far as I know, needs continuity of some sort. So I don't know. If someone knows, by the way, they can say anything. Okay, so we are starting with the neural network part. So explaining neural networks from ground zero is very hard. So I will try to make this as an example. We will go through it through an example to familiarize. So suppose that you want to brew the best tea for the seminar. So you want to have the best tea. So you have your factors to have the best tea. For example, it can be about the brewing time. I will draw a circle, suggestively a circle to represent those. A brewing time, brewing temperature. What else? I said pH of the water. By the way, if I switch this, is better. Okay, it's better. So I have drawn three circles right now. For example, amount of minerals in water. It can be there can be lots of calcium in the water, which is not very ideal for the black tea. Also, maybe the brand of the tea leaves, which also is very significant. So we can enumerate all those states, which the four of them was already in numbers, but the tea brand was not. So we can call, for example, tea brand 1, tea brand 2. So you can convert anything that you want to numbers in this case. So we want to have actually make a system that will say whatever which parameters are going to be the most the best for the tea of the seminar, for example. So a very simple system is to just apply this kind of thing, which I will explain what it is, to acquire taste. This is the taste, for example. The taste in this case is not an objective function, but it doesn't matter. For example, it can be your taste. It doesn't matter right now. So our very simple model just takes 5 inputs, and so relative to their importance, you multiply them by some weight. For example, if what did I say? Brewing time can be 4 times as important as something unit that has a unit weight. Brewing temperature can be even more important. Some others can be less important, maybe. It doesn't matter. So in this our very simple model, you just weight them and add them, and this is like a linear combination. I call this weight W1, W2, etc. and these as A1, A2, etc. So what I have is W1 times A1 plus this, which there is a neater way to write it. The neater way to write it is as vector form. So we can write it as R A1, A2, A3, A4, A5, and multiplied by if the W's are also as a vector, W transpose, for example. But if it's a row, just W. It doesn't matter. So we will have a number in this in the end. And this will be a very simple model, and it may not capture the complex relations with respect to taste. It cannot, of course. But I want to improve on this model. What can I do? I can maybe increase the parameters in this case. But these parameters are meaningful right now, so I want to keep them. What can I do still? Maybe I can add another layer. Another layer will increase the parameter size. So let's let's do that. Let's increase the parameter size. For example, I have three activation. No, by the way, these are called neurons. It's related to brain, but this history part is very long. So I'm just going to a very, very simple example to demonstrate the simple ideas. So you have to connect anything with everything, and this is you probably a familiar picture that you have seen before. So our case is this. Actually, I didn't talk about how to learn these parameters at all, but suppose that we have learned something which is very maybe useful in our case. We actually don't know in practice about the intermediate layer, what it means and what it learned. This is called the hidden layer. But as a demonstrative thing, let's suppose it's kind of one layer of abstraction. So one layer of abstraction, I can demonstrate as, for example, I have the pH of the water, the brewing temperature, brewing time, etc. Maybe those influence other things, which can be, for example, the lightness and the color, the bitterness of the tea, and the freshness of the tea, for example. So those can determine these, and this determines this. So it actually adds a layer of abstraction. But as I said, we cannot be sure about what it learned. So this can be our guess. It may learn some composite things, and those composite things can help this to approximate even better. But there is a problem. As I said, it's looking like a matrix multiplication in this layer. If I multiply another matrix to here, for example, this is the so of course we have to have lots of parameters. But suppose that we are interested in the output of this, for example, now, and it will be of the form of this right now. But if I then for the next layer, I will have to multiply it with another matrix. For example, let's call it V2, and this is V1. But we know that V2 and V1 is just another matrix. So composition of two linear operations are another linear operation. So it's not very useful because I try to increase the parameter size. I want to learn more things, but it still keeps to have same kind of an object. It's just a linear operator. So what do I do in this instance? By the way, one thing that I missed, that I didn't say, was there can be biases. For example, my brewing temperature can be 0 degrees, because this is my arbitrary unit. But 0 degrees doesn't mean that it doesn't have an effect. It has a big effect. It's a cold tea, so it will not be an ideal tea. So how to make this, how to show its effect on the output, we have something called bias, which is a constant amount, just B0 for example, which is also a learned parameter, along with the weights. We learn the weights and the biases. So this picture is getting more complicated at any second, which I wanted to do. So this is also not useful, as I said. So one very simple thing to do is to actually add a non-linearity on this output. If I have a non-linearity on this output, then when I multiply it with the second layer, I will not have any another linear operation. So this is very useful. This gets what I wanted. So we denote the nonlinear operation as sigma. So this is a known function that you choose, and there is the other layer. And actually, if you follow this nicely, you can increase it to any layer as you want now, because these concepts generalize. Of course, there are problems if you increase the layer size. There can be numerical problems, and so it's about the machine learning lore, which is not very important again in this instance. So we have our neural network overview. Is there any questions about this model, which is called multilayer perceptron? There are lots of different neural network architectures. This is the most easy one, and still widely used, by the way. Even in ChatGPT, there are those. Okay, is it something good that you don't have questions? I'm not sure. So let's talk about auto. Auto differentiation is a very useful tool that we are going to use as in LNNs, and I denoted as LNN Lagrangian Neural Networks, and also in the gradient descent algorithm, which I didn't also talk about, which is about it's an algorithm about learning the weights and the biases of the system, and it has to have the auto differentiation inside.
What do you mean by learning the parameters?
So you actually, for example, we had 4 seminars before, and I, for example, noted the tastes of them with my parameters, and there are 4 cases. It's a very small number, but if we had, for example, 100 seminars, I would have 100 inputs and 100 outputs. So my goal, the learning means in this case, I give the inputs and outputs to the neural network, and it tries to optimize this taste parameter with tweaking the weights and the biases of the system. I didn't say how it does that.
So the system does find the weights and biases so that it will minimize the given input-output differences.
Yes, that's a good point, which I have to mention. I have to define a loss function. This is called a loss function. For example, my denoted taste was about, for example, in a particle set of inputs, it was, for example, 9, but my network actually predicted 7, for example. I can denote some kind of a difference of diverting from the truth. It can be the differences, it can be the square of the differences, which is very likely done. It's called mean square average. So let's talk about the auto differentiation part again. So I want to know, for example, how much my taste depends on the pH of the water, for example. I denote this as the pH. I want to know when I change the pH of the system a little bit, how much it will change the taste. This is my problem. So, as you know, pH actually goes through all the layers. It influences all the nodes in the next layer. Then, if there are more layers, this is going to continue. But in this case, they are also going to influence this taste. So taste is influenced by pH by different roots. Let's look at the roots. Like one of them is this, one of them is this, and one of them is this. There are 3 roots of influence. If you have seen, as you have seen in calculus, this is a very related concept. This is looking like the chain rule. So if you want to know, this is that. If you want to know, for example, how much my taste depends on the pH, I just want to take the derivative in this instance, and this is going to depend on the chain rule. For example, taste derivative of the taste with respect to the let's call those, I don't know. What should I call those? X. What?
A1, A2, A3.
A?
A1, A2,
A1s are this, so it's reserved.
Features.
A5, A6.
Okay, H. Let's call it this way. H. Times H1 times A4. This is A4 in my definition. So this is what does this do? It denotes the. Thank you. So this denotes the method of influence through this if I also add the other one with H2, it's going to be this. So this is very intuitive. This is a very intuitive concept. So you have your chain rule, and this is how it looks. So let's see if I can actually find out this. If I look at this formula, everything is actually known. So I can take just this because I know that it's just linear function, and on top of that there is an activation function which I also know the derivative of. So I can just know this. And also what is different for this? There is nothing different for this. So I can also know this. So there is everything is known. You can construct an algorithm to find this chain rule, and you can actually know the whatever derivative that you want in this instance. So that's what is called as auto-differentiation. You don't calculate those explicitly in your hand. You just give it to the computer, and it does that. And this is very useful for the learning part and also the Lagrangian neural network part in this instance.
Is this the same thing that we call as backpropagation?
For backpropagation, we use auto-differentiation. So if you have lost this many of people, you can give them papers to do backpropagation, but it will take lots of time. So you just give it to the computer. So yeah, this is just a method to do that. Lagrangian networks are going to also have to use this or maybe you. So this is actually enough background. We are going to start the Lagrangian network part, and I will call for if you want to have refreshments or if you have any questions about the background. Now please ask.
Just to make an addition to the previous question, he asked about the summation and integral sign in front of Lagrangian. In physics, the time is continuous, it's not discrete. So the Lagrangians we have in physics are the actions in physics are integrals because we have a continuous time. So it should not be discrete.
Yeah, even in the quantum mechanics, we treat the time as continuous as well as the space.
But it's not that important because we don't complete the action usually.
So I got very hot. Okay, now we are starting the Lagrangian neural network part. So this is from 2020 from Miles Kramer, which does lots of things that I love in general. Actually, symbolic regression was through his package called PySR, which stands for Python Symbolic Regression. So let's dive into this. So this is the most default example that we had. This is the double pendulum that we saw. So this has very low FPS, but here it seems good. So this is a double pendulum, which is very chaotic, and it's very hard to calculate in general. So my base problem for all this is given q and q dot, which means, as we remember, position and the velocity, we want to know the acceleration. Why do I want to do that? Because if I know the acceleration at one point, I can just know how much the velocity is going to change in the next instant, and if I know the velocity, I also know how much the position is going to change in the next instant. So by knowing the acceleration, I actually can continue my particle's trajectory. So this is my problem, q and q dot, and find the q double dot. And yeah, the immediate use of this problem, if I solve this problem, then I can just simulate what I have as a physical system using integrators, which I didn't say what it was, but it's about, for example, if I have this particle, then integrator does something about taking a constant, very small time amount and tries to calculate the next instant. So it can continue through that. Stop. So yeah, let's think about a basic solution to this problem. We can use a neural network. This neural network, for example, can work, maybe. This is the position, this is the velocity, you input this to the network, and you want to hope that it outputs acceleration. So it can work, but it has some problems. So you actually also define the loss as Q predicted, this is this for this, and Q true as you know the you have to give some training data to this neural network. So you can calculate also this. So this might have worked. That previous method might have worked. What Lagrangian neural network does is what was the problem? I want to know the Q double dot given Q and Q dot. Actually, I know Euler-Lagrange equation, and if I reformulate it a little bit, I can actually get the expression with respect to the Lagrangian, actually not Lagrangian, Lagrangian's derivatives. It's an easy concept to, it's an easy calculation to carry out, but I have to have a time-independent Lagrangian for this to be true. So Lagrangian neural network actually uses this knowledge from physics, from Lagrangian mechanics, and I have another neural network which takes Q and Q dot and outputs a Lagrangian. I don't know about the Lagrangian. I don't have any training data on Lagrangian. What is going to be how this is going to be useful? Well, if I have a Lagrangian, then I can actually calculate the derivatives, as I said, with auto differentiation, and actually I can calculate the acceleration, and the same loss applies. So I can start with random weights, and then also hope that my network is going to learn the correct Lagrangian in the Lagrangian correct Lagrangian family, because there is not one, to actually have nice predictions about this acceleration. This is my hope in the Lagrangian neural network. So what is the advantages of this approach? This is from the paper, Lagrangian neural network paper. As they have shown, when you increase the time, it seems like the baseline is, by the way, what I showed 2 slides ago. As it seems, energy seems to be not conserved if you increase the time. But in LNNs, it continues to be conserved for a long time.
What is the baseline? Can you say
Baseline is the
just predicting the Q double prime and getting the difference. It's this.
It's this.
Okay.
Baseline is this.
Okay.
By the way, they interchange curves and absolute values as for the system. So it seems like Lagrangian neural network in this instance works better and conserves the energy better. How does it do that? Well, we have actually baked physics into our neural network. So our neural network is not something that I always imagine the neural networks as, for example, if I watch a pendulum and I close my eyes and try to continue the motion from my brain, it will be true for some time, but it's going to be less true if you increase the time in your head simulation, because you don't have any physical laws baked into your brain. But Lagrangian neural network has something baked into it, because I calculate the acceleration with respect to the Euler-Lagrange equation. You cannot violate the Euler-Lagrange equation in the Lagrangian neural network.
Can I ask you a question?
Yes.
Are we here trying to model an ideal system of double pendulum that there is no, like, really no loss of energy?
We are only modeling a time-independent Lagrangian, which, as what you said, is in the set of what we are trying to know. But it can be, for example, just a falling object, or maybe.
No, for this specific case.
Yeah, for this specific case, it's from double pendulum. This graphs are from double pendulum, but
Okay,
it
but
doesn't
this
have
double
to.
pendulum is in a frictionless environment.
Yes, it has to be a time independent, which means, of course, you can reverse the motion. Yeah, this is a condition.
Okay, and another thing, we are after the scalar value of the acceleration, right?
What I showed is just one dimensional, so yes. But for n-dimensional case, you have to formulate those differently, and you will get actually direction as well.
Okay.
I also have a question.
Yes.
I couldn't catch what's the difference between the baseline model and the LNN. They look the same in the two slides.
They are not the same because you just put the Q double dot to here in the
As an
baseline,
output.
but in the other one, you have Lagrangian as the output. Then from Lagrangian, you apply this formula to get this. So you have to go through that Euler-Lagrange in Lagrangian neural networks. This is,
So only the loss function changes.
loss function is the only thing that is the same. This is the same with same loss function with before, but what it predicts is different. This predicts Lagrangian. Then you differentiate the Lagrangian and do this formula to get the acceleration. Then you plug this to the loss function. So very different. So, yes.
So this claims that Lagrangian is easier to predict for neural networks, right?
Easier than what?
Than acceleration.
Maybe not easier, but maybe more useful. It doesn't say that it's more easier.
Probably not definitely easier.
It's not
because
easier.
of the calculation steps.
It's not easier because of this. There's also this.
But
the-
it's a final step.
There
I
is-
mean, the
there-
neural network itself must be more complex with this approach. I suppose I'm not sure.
Yeah, of course, training time also increases with this approach, but the most, I will come to the negative parts, so I will mention it there. So shortcomings is, first, it doesn't work with time-dependent versions. Actually, there is an extension, generalized Lagrangian neural networks, which was out this year. And we actually plan to do this project first, then we changed the plans and hope it was for the good because they have done it in the instance that we thought in that case. And training can be very unstable. This is the most problematic part because in our Lagrangian, in this formula, there is second derivatives, and second derivatives can be as large as you cannot predict. So you cannot normalize that second derivative. If you normalize that second derivative, then you actually destroy the physical information about this formula. So because of those weak values, this is very hard to train. And actually, in my attempts to simulate the double pendulum, we couldn't do it. And in the literature, they also couldn't do it, the double pendulum part. You have to have very specific steps to overcome this problem. This is a very hard problem. But there are also advantages, and this is just an example to actually motivate you to another thing. So it doesn't matter.
Can I ask you a question?
Yes.
How do we get the training data? By doing high precision simulation of the physical system?
It can be from cameras or maybe simulations as
So
well.
by cameras, then it means from real physical system.
Yeah, it can also be that. You can have a higher FPS and calculate the
Okay.
positions and velocities. And
Is this Lagrangian concept applicable to small particles also like electrons? Or
Lagrangian concept is applicable, but Lagrangian neural network concept probably is not, because
so I have more other philosophical question. Q prime, Q double prime, you need that data for your training, right?
yes,
But there is some problem there, like if you know the mass accurately, you cannot know the velocity that much. Or you know the velocity, you are not knowing the mass that much.
yeah, in quantum realm, this formula has to be very different. So we are usually in this neural network, we are in the classical range.
Okay, we
So-
are in classical.
Yes, yes.
Yeah, Lagrangian is completely different in quantum.
Yes, yes. There is not a path in quantum. Quantum. There is not a path that particle takes.
Yes.
So
Uncertainty, yeah.
whole thing is very different. So what I have done additionally to Lagrangian network is getting a mathematical equation out of the Lagrangian neural networks. So I do this with the symbolic regression, and let's see what it is. So for example, so we just give input and output pairs to the symbolic regression machine, and hope that it will calculate what function generated that input and output. For example, I have inputs 1, 2, 3, 4, 5, 6, and the outputs are this. So your brains can recognize what this pattern can be, which is a spoiler, 2 times n squared. So the hope is that symbolic regression will also going to be finding this connections between inputs and outputs. So I have used that. There is
That is for order 2. There is also another solution for order 6.
of course. The solution is not absolute. There are error terms and plausibility terms. For example, if you complicate your prediction of the function,
So
it
you
will
will
be
for the simplest one.
yeah. It will you have to optimize for simplicity and accuracy. Yeah, but you don't do that when you're using this because it does that automatically again. So yeah, I had this in the Lagrangian neural network. So I didn't know anything about the Lagrangian. I just knew about position and the velocity. But after the training, I have this. So I can actually generate Q and Q dots as random, and also have the Lagrangians. So I can actually generate inputs and outputs of this. Then I can actually input this to the symbolic regression. And for example, from my project, I had one of these harmonic oscillator which was easy to train. So the Lagrangian is like this in our case, and this is the time, this is the value, just oscillating sinusoidal. It's an easy one. So yeah, this is the known Lagrangian. I plotted this in a 3D way. So this has kind of a Pringles shape. So what I found in my project was this. So is it very bad? No, it's not very bad because it's just the -1 multiplied by -1. And as we have shown, it doesn't matter. The coefficients doesn't matter. It can be multiplied by -1 or additive to anything else. And the Lagrangian predicted was this. So as we said, it's not important. This is not important. And this is not also absolutely important. What matters is the ratio of those. And it's very similar. It's very, very similar. There is a very small error, but my approach was able to actually find the underlying Lagrangian from just observing the harmonic oscillator. So what means to be knowing the Lagrangian? It means everything in classical mechanics because you can calculate momentum, energy, or angular momentum, anything you want out of this. So this is a very important step. So what did we achieve in this case? Only from the position and the velocity data, we have learned the Lagrangian, which was the central object. I can use this on unknown systems to infer symmetries or anything else. For example, I can watch something with my camera and then input this to my machine and predict its Lagrangian. Then say, for example, this Lagrangian has those properties and it doesn't have those properties. So I can know about the theoretical aspects of the system by just observing the system. So this is a very useful concept. So Lagrangian neural networks are actually physics-informed neural networks. It's a broader family. The definition is that they are neural networks that embed knowledge of anything, any physical law inside the learning process. What I did was to actually to just put acceleration. I knew acceleration from Euler Lagrange equation, and I baked that equation to my neural network. So this is also a case of physics-informed neural networks. So is this useful for theoretical physics? Can I do theoretical physics with it? Well, certainly not with the Lagrangian neural network because it's a very limited thing. But in general, with tools like this, which I think I showed something. By the way, yeah, with this Lagrangian, I might have predicted the gravitational law, very simple, like quadratic, and also electromagnetic laws, very simple ones, Coulomb ones, Newton's ones, by just inputting the falling objects or attracting forces, and I would have had the Lagrangians that I wanted. So I would have known the quadratic form of that. So yeah, although Lagrangian neural networks are not stable, there can be tools like that for different things. So this is, for example, an example which doesn't work. Okay, yeah, it works. For example, again the same guy, which is my favorite. His challenge was to actually rediscover orbital mechanics with machine learning. So his challenge was to know this just from the data, and I will not go into that, but he did that. Yeah, this is in principle possible, and it's not just for theoretical physics. For outside of theoretical physics, this is also physics, but applied physics. You can simulate quantum systems with classical computers with neural networks. Usually, by exact calculation, you have to have exponentially many parameters, but you can have polynomially many parameters with the neural networks, and it will have a nice accuracy. My internship was about that in summer, by the way. Also, there's things like AlphaFold. It has won the Nobel Prize in chemistry this year. It's the thing that predicts protein folding structures from the I don't know where, but data. So this is also used for drug discovery and other stuff. So there are lots of things in the other fields as well. So this is a very promising thing, and yeah, many more. So will AI actually help to discover new physics? This is like the big question. So Stephen Hawking said yes, and he said that physicists aren't going to be discovering that. It's a very bold claim, and I actually don't think that it's going to be like this. I think this is my opinion. Using the computational power of the computers to recognize patterns is greater than humans after some point. I cannot, for example, understand the millimeter oscillations of a system by looking at it, but AI can do. So I can use this AI techniques and other computational methods to actually maybe have some idea of what patterns are there in my data. So this is a useful thing. Also, our instruments are becoming more sensitive and the data is becoming more enormous. For example, 2 weeks ago, the discovery of the pulsar scheme, if you have went to that, there was like meters of data and she looked every part of that. You cannot do that right now. For example, discovery of the Higgs boson. There are more data than what you can take as one human in your lifetime. So you have to have some kind of shortcuts to actually do that. And my hope is that, actually my end goal is that, maybe there can be a system by just looking to the data, it can predict how should you approach that problem. Maybe, for example, in particle physics you use group theory. And maybe somehow there can be a tool that says, it looks like the symmetries are from this group. And it can lead to the correct answer somehow. So this is the hope, because if we get assistance from these computational methods, maybe it will be easier for us to discover. I still believe that physicists are going to discover, not AI, but it's going to be like an assistant relation in this case. And yeah, this is the end of the seminar. The Q&A section is there, and there's all the links and resources inside the description of the Google form, and you can write anything you want about the seminars, if you have liked or not. So yeah, questions?
During the prediction of the Lagrangian, do we need to know do we need to assume a form for the Lagrangian before we use the neural network? Because if you are not expecting the third derivative of position in our Lagrangian equation, then we are not going to be getting the third any terms for that.
Maybe you can extend this question, like, what do you mean as a Lagrangian as an output?
So Euler-Lagrange equation, as I shown, has quadratic. There is not third or fourth derivatives. So there is an assumption for like this. But this assumption is generalized for field theory, general relativity. You discard the other parts to get what you want. So in classical mechanics, you don't expect some third derivative popping up. And also, the third derivatives are unstable solutions, except in very stable, in very special conditions. So we don't see that. We don't see them in nature usually. But we are actually assuming some form. And one thing is as well time independence in our Lagrangian network. But they have generalized that. So yeah.
Do you think LNNs can be a useful tool to achieve AGIs? Because it can, I think, like help robots predict the movement of objects around them and have a better physical understanding of their environment.
Because of the instability, no. But as some tool like that, I don't think AGI. I don't know. My personal opinion is that we will not understand AGI if there is one as well. So how can we confirm that it's AGI? It will say that it's, I don't know. So that was also.
Okay, thank you for the nice talk. I wondered, is there any approach that uses findings path integral methods? It's like
I couldn't hear.
path integral method. Is there any approach that uses like neural network approach? I don't know, and that uses the Feynman's path integral method. It's basically some overall possible paths.
I didn't explicitly see that, but I think there is one, because anything that I search is at least at some level thought. For example, anyways, yeah. I couldn't find a truly creative thing in this.
From this talk, my take-home messages, I guess, I hope it's correct. Instead of forgetting everything that we know, let's also use them as a mediatory step and try to estimate that, try to find that. I mean, if you know some physical phenomena, why you should just focus on the last output that you want. Try to get that and then apply the formula. Something like that, I guess.
Yeah.
Maybe it can be Lagrangian, or maybe some other physical phenomena that you can integrate with similar approach to the LNNs or some PLNs, whatever. So let's not get dumb and try to integrate our cumulative knowledge to the current knowledge.
Yeah, I cannot speculate about what's going to happen. Maybe the systems that we don't know anything about can be more efficient. So I don't
And
know.
one more thing that related to that, can you come back to one previous slide? For the first bullet item, I guess you need to add something like, if you also have some explanation from the neural network. For
Which one?
computers. Using the computational power of computers to recognize patterns with some explanation if possible.
Yes, of course. But I mean,
Otherwise, just estimating the second derivative is also getting the pattern, recognizing a pattern.
of course, yes, meaningful patterns.
Yes. Explainable.
First of all, that was a very nice talk, very informative. I've learned a lot. Thank you for your presentation. Like, as I understand, like these tools will get us to like equations, which is a great thing for discovery. But if you look at the history of physics, they have their like internal understanding of the universe, and mathematics is just a tool. So like they have like these people have predicted things that cannot be even validated and experimented, and then later we saw that they were right or wrong.
Yes.
So in that sense, I would like to learn about your comments, like getting the like exact equation. I know that it's not exact right now, but getting this is great. But like, how much of a I mean, it's something valuable. But how do you think it will help like the real physicists?
So, for example, in Lagrangians, if you know Lagrangian, you actually can infer the symmetries of the system, for example. And symmetries is it's a very physical concept. So it's above the just equations. So there's that.